Hi, and welcome. Today, we have a very interesting derivative here. We are going to be differentiating with respect to x of x to the x. Okay, seems like a pretty easy problem. Let's just use the power rule. I mean, it's in the form of x to the something, so we see that as a power number here, so which is just x, so let's just bring it down -1, so this is equal to x times x to the x minus 1 using our indices properties. We know that if we have a to the m times a to the n, this is equal to a to the m plus n. So this is going to be, we can see that x is x to the 1, so it's x to the 1 plus x minus 1 power, so the 1 and -1 can cancel out, so it's just x to the x, and we are done. Thank you so much for watching. Don't forget to hold on. Something's wrong. One thing that's wrong is that 0 to the power of 0 is not defined. So when we differentiate x to the x, we should expect that the derivative when we sub in 0 is undefined. Okay, I guess it works, but according to what I see on Google, that's not the same thing. So there's maybe something else wrong. What could be wrong here? Let's look back. We used the power rule. When we use the power rule, it states that if we have the derivative of x to the n, where n is a constant, this will be equal to n times x to the n minus 1 power. But the problem here is that the power in this case is actually a variable. It's variable x. So we cannot use the power rule. So maybe you can just use the exponential rule. So like, if it's like in the form of a to the x, like that, it would just be ln of a, then the quantity times a to the x, right? Well, same issue here. A is meant to be a constant. However, our base is a variable. So we cannot use any of these properties right away. What can we do? Keeping in mind that later on when we differentiate and substitute the value 0 in, it should give us an undefined value because x to the x is not defined at x equals 0. Well, let's use a little bit of logarithmic properties. What do I mean? Recall that if we have a to the power of log base a of b, we get that back b. And we know that we can differentiate e to the power of something. So how about we re-express x to the x in the form of e to the power of something? Namely, we are going to be re-expressing this as the derivative with respect to x of e to the ln of x to the x. Another property that we know is that if we have log base a of x to the n, n can in this case be a variable. This is the same as n times log base a of x. So it's kind of like we can bring down the power when we have a logarithm. So what we can do is we can see this x and bring it down. So this is going to be the derivative with respect to x of e to the power of x ln x. This is something that we can differentiate. So let's differentiate this. If we have the derivative of e to the f of x, where f of x is just some function of x, this is going to be equal to e to the f of x times f prime of x. Meaning, we are just going to copy the same thing again, then multiply by the derivative of the power. So, what we can rewrite this as is this. It's just going to be, the derivative is just going to be e to the x ln x times the derivative with respect to x of x ln x. What can we do? Well, we see that we have two things being multiplied together. We have x and ln x. Recall that if we can use the product rule, if we have the derivative with respect to x of f of x and g of x, then this is going to be equal to f prime of x g of x plus f of x times g prime of x. Okay, so this is going to be equal to e to the x ln x times this thing. The derivative of x is going to be 1 because we can see x as x to the 1. When we differentiate, we are going to bring the power down, minus 1, so it's 1 x to the 0. Anything to the power 0 except for 0 to the power 0 is 1. So this is just going to be 1. And then we are going to copy ln x. Next, we are going to be adding x times the derivative of ln x, because it's g prime, as you can see right here. The derivative of ln x is going to be 1 over x, so we just write it down. Okay, let's do a little bit of simplification. We see that we have x being multiplied to 1 over x. The x can cancel out. The 1 is being multiplied to ln of x, so the 1 doesn't really matter. And we know that e to the x ln x is equals to e to the ln of x to the x, which is equals to x to the x. So we can actually just rewrite this as x to the x. The reason why we know this is because we took x to the x and re-expressed it in the form of e to the x ln x in the first place. So this is just going to be x to the x times ln x plus 1. And that is pretty much the correct answer. Well, it does satisfy the condition when we have x is equal to 0. This is indeed not defined because we have x to the x. So if we sub in 0, this is not defined. Okay, how about another method? Now we are going to be using a different method called implicit differentiation. This may be foreign to you, but just go along. Let's just go along with it. We're going to let y be equal to x to the x. When we let's take a ln on both sides. Using the logarithmic property, we can bring this power down. So this is going to be ln of y is equal to x ln x. Okay, now let's differentiate both sides with respect to x. The derivative of x ln x, as we have discussed just now, is going to be this thing right here, which will simplify to ln x plus 1. So let's just write ln x plus 1. The derivative of ln y with respect to x. Well, we initially expressed y in the form of x. So y is a function of x. If we let ln y be z, then the derivative of z with respect to x would be equal to the derivative of z with respect to y times the derivative of y with respect to x. This is the chain rule. So we can first differentiate ln y with respect to y, which is equal to 1 over y, then times the derivative of y with respect to x, which we don't know, so we will just leave it as dy dx. One thing to note though, we wanted to find the derivative of x to the x, and we defined y to be equal to x to the x. This means that we essentially want to find dy dx. So perhaps we can solve for dy dx. Well, just multiply both sides by y. You get dy dx is equal to y times ln x plus 1, and we know that y is equal to x to the x. So therefore, dy dx is equals to x dx times ln x plus 1, which is what we wanted to find in the first place. This corresponds with the solution above, and so yeah, this is pretty much correct. Thanks for watching, and I'll see you guys next time.